Hi everyone. In this video, we're going to see how integrals can be used to calculate the length of an arc. So here's the question we want to answer. If we were given the graph of a function, such as the one you see here, how can we calculate the length of the curve? It would be difficult to measure unless we had a way to straighten out the curve, but we can't really do that unless this were like a physical object like a string. But thankfully, it turns out there's a simple formula we can use for this, and here it is. I'm going to use the letter S to represent the length of the curve, and it turns out the length is equal to this integral. You'll notice that A and B here represent the interval on the x-axis. What we see here is a dx integral, but it turns out you can also calculate length using a dy integral. And for that, all we need to do is interchange the rules of x and y in our formula. Just be careful that the integration limits should then represent y values. So let's label the endpoints as y equals c and y equals d. And those values would represent the limits of our dy integral. So we see there are actually two different formulas you can use for calculating arc length. Generally speaking, you'll use the first one when you're given a function y in terms of x, and you'll use the second one when you're given a function x in terms of y. We'll look at some examples as well later on in the video. But before we get to an example, I want to provide us with proof that these formulas I gave us are actually correct. So given that the formula involves an integral, you can reasonably expect that length is probably going to be calculated by slicing up the curve. And then we could add up the length of each segment to get the total length. So that's exactly how we're going to do it, a very similar approach to what we did with area and volume so far. You'll notice that the segments I've drawn here don't exactly match up with the curve. But that wouldn't be such an issue if I cut the curve into a lot more pieces so that the segments are much smaller. The ideal situation would be that these segments are infinitesimally small to give us the greatest amount of accuracy. So let's call each segment ds to reflect that. Of course, the segments I've depicted here are not actually infinitesimally small, since I couldn't possibly depict that. So just imagine that I've exaggerated them to increase visibility. We know the total length would be found by adding up, or in other words, integrating all of these pieces that we just called ds. So the only thing left to do would be to calculate the length of each piece. Notice this length could be found by considering the rise and run corresponding to each segment. And the run really is a change in x, and since this is an infinitesimally small segment, we could call that dx. In similar spirit, we could designate the rise as dy. After that, we could apply the Pythagorean theorem to get the length ds. Now, in order to get this to look more like the formula I gave you, the next thing we're going to do is factor out the dx squared from both terms. You might be bothered at this point that we're treating dy and dx like they're actual numbers, and that does require some theoretical justification, but it's not very illuminating, and we can trust that those details have been checked for us, so let's just go ahead and do it. It's not so bothersome when you think about dx and dy as representing actual quantities of rise and run. But anyway, now that we've factored out the entire first term, all that remains there is a 1. The second term is a bit trickier since it didn't contain a factor of dx squared to begin with, but factoring something out is equivalent to dividing it out, so we could do it like this. If you're not convinced, you could check this also by expanding all this back out again and seeing that it really is the same thing as what we started with. Now, since we have two factors that are multiplied, we can apply the square root to each of them separately. But keep in mind that this is only valid when the items are being multiplied or divided, not when they're being added or subtracted. Okay, in this case, my two items are being multiplied, so this is a valid step. And we're going to write our fraction as dy over dx all squared, which we can do because that power of 2 is attached to both the numerator and denominator. Now, here's the real reason we factored this out. A simplification can be made here by canceling our root with our square. Now technically when we do that, we should have a plus or minus sign, but since dx is a positive quantity, there's no need for the plus or minus here. So we're left with this formula for ds, and if we insert that into our formula for the total length, we can now see the result that I gave you at the start of the video, which completes the proof. Well, this is the proof of the dx formula, but the proof of the dy formula is pretty much identical to this, and you can check the details of that for yourself if you like. Okay, so let's try to actually use this formula to calculate the length of a curve. The question tells us that this curve extends from x equals 0 to x equals 1, so we're going to use those as our values of a and b. And now we need to figure out the formula for dy over dx. That notation should be familiar to you. It represents the derivative of y with respect to x. So for that, we need to look to the function we've been given and take its derivative. That's pretty simple in this case, just use the power rule. It doesn't hurt too to just make a few cancellations here and simplify, but now we can take this derivative and we can insert it as dy over dx, which completes the formation of our arc length integral. You might choose to write it this way in simplified form instead though. We've just seen that applying the arc length formula is actually very straightforward. All you need to do is insert your endpoints as integration limits and include the derivative of your function. The tricky part is that the arc length formula tends to produce integrals that are really challenging to actually calculate. And that's because square roots are difficult to anti-differentiate when they contain multiple terms which are added together like this. Unfortunately, like with most other integral problems, there is no recipe I can give you that will work every time, but I'll show you some strategies you can add to your toolkit that could be helpful at least once in a while. First, notice that this negative exponent indicates the existence of a denominator, so more specifically, this can be written as 1 over x to the 2/3. And now I wouldn't normally advocate for common denominators when finding integrals, but it can be useful to do that when you're working under a square root. Let's try it out and see why that is. So in this case, this is what our common denominator would look like. And the real advantage of doing that is that we know a square root can be applied to the top and bottom of our fractions separately. And if we do that, our denominator can then be simplified to x to the 1/3 if you apply that square root. And why is that important? Well, it's because the x to the 1/3 resembles the derivative of what's inside the square root, right? If you take the derivative of what's inside the square root, it would be x to the -1/3, which resembles what we see in the denominator. And that strongly motivates the use of a u substitution. Let's give it a try. So if we declare u as the inside of our square root, then du is calculated by taking the derivative as shown here. What you'll notice is that du contains this factor of x to the -1/3 dx, and that is something that also appears here in our integral because of that denominator. We've seen that this type of pattern can make for a nice substitution. But to complete that substitution, let's rearrange this formula to see what that 1 over x to the 3rd dx is equal to. With a bit of basic algebra, you can see that it's equal to 3/2 du. So that means this entire expression I circled in red can be thought of as 3/2 du. And putting all of that together, we can see that this can be expressed now as the integral of root u times 3/2 du, which is actually a pretty nice result. But don't forget that we still need to change the limits into values of u. We can do that using the formula we declared earlier. Just plug in the old limits of 0 and 1 into that formula to get your new limits. You can check that these simplify to u values of 1 and 2 respectively. And for simplicity, I'm also going to pull out that constant factor. And also, I'm going to express root u as u to the 1/2 to set myself up for the next steps. The rest is pretty straightforward from here, so I'll leave it to you to check the remaining details, provide an answer of root 8 minus 1 units of length. Don't forget that we actually have two different formulas for arc length. I just showed you how to use the dx version, but let's try the same example using the dy version instead. Don't forget that c and d in this formula represent the y values of the endpoints, so we need to figure those out still. But that's no problem because the y values are found by plugging in these x values. So that gives us our c and d values. And as a next step, we would need to figure out the formula for this dx over dy. What that represents is the derivative of x with respect to y. And for that, we need to think of x as being dependent on y rather than the other way around. So the way we do that is we rearrange this equation to get the x by itself. But that's just some simple algebra. So start by multiplying both sides by 2/3, and then apply an exponent of 3/2 to both sides. And you can check, pause if necessary. You can check that this is how you get x by itself. And with that, we're ready to get our formula for dx over dy. That just means take the derivative, except now we're thinking of y as our independent variable. Now, the derivative of something which is raised to the 3/2 would be 3/2 of that something raised to the 1/2, right? All I did there is apply the power rule. But since the something inside the brackets is not just a y, the chain rule needs to be applied here. And that would tell us to multiply by the derivative of the inside part, which would be 2/3. Okay, now we can make a couple cancellations to clean this up a bit, and then with that, we're done getting dx over dy. So now just sub that into your formula for s, and our integral is ready to be calculated. There's a couple obvious simplifications to make first, such as multiplying these exponents to make them cancel, and we might as well clean up our integration limits too. All that remains is to calculate this. Pause and think about how that should be done, and when you're ready to be spoiled, let's have a look at the answer. The most straightforward way to approach this is just starting with a u substitution. You'll notice in this case that the derivative of the inside part is just a constant, so that won't cause any complications for us when calculating du. If you give that a try, the details actually work out pretty nicely. So I'll leave it to you to check that all of this does provide us with an answer of root 8 minus 1, which matches the answer we found before. What you'll notice though is that although the dy integral required a bit more setup, the payoff was that the integral we ended up with was much easier to calculate than when we did it as a dx integral. So the lesson to take from this is that if you use the dx formula and find the resulting integral is really challenging, it might be worth your time to try using the dy formula instead. You have two formulas to work with, so you should use that to your advantage when necessary. That's all I have to say about arc length, so I'll end the video here and I'll see you next time.